In this video we'll look at exercise 7b, which takes us through integration involving the inverse trig functions. Remember, a function has to pass the vertical line test, and if we have the sine curve, which is partly shown here in blue, that sine curve, a transverse wave, will always pass the vertical line test. But in order to have an inverse, then it must be reflected in the line y equals x, and then that reflection must also pass the vertical line test. So therefore we need to consider a restricted domain. So if we were to consider between minus pi on 2 here for x and up to pi on 2 here, then that curve, when reflected in y equals x, gives us that green curve. That green curve is also a function. So if we have y equals sine of x on a restricted domain between minus pi on 2 and plus pi on 2, that does have an inverse, and we call that y equals arc sine of x. That's the same as sine minus 1 of x, but we no longer use that notation. Now, the domain of this new green function will in fact be the range of the original function, the sine curve. And the range of the sine curve, the blue curve here, were between 1 and minus 1. So that becomes the domain for that green inverse function. Now, if we consider y equals arc sine of x, if we were to rewrite that as x being the subject, then x would have to equal the sine of y. Remember, if you have y here, if you wanted to get the sine away from this expression, you'd take the inverse sine of the other side. So sine minus 1 of x, which becomes arc sine of x. We've seen that back in year 9. Alright, so I have this function here, which I'm going to differentiate with respect to y. So dx on dy becomes, now if we differentiate sine, we get cos. So we get the cos of y. Now I want to express the cos of y in terms of x. So remember that cos y is equal to the square root of 1 take sine squared. And that comes from the sine squared plus cos squared equals 1 formula. And now doing that, I can replace sine squared y by this expression here as x squared. So we're left with the x on y equals the square root of 1 take x squared. Now, the chain rule you have seen in your math methods, the y on dx on dy, they're not fractions, but they in fact function as fractions, and that would simplify to give us dy by dy, which is equal to 1. Which would therefore mean that the y by dx and the x by dy are in fact reciprocals, because they do multiply together to give us the result of 1. So, if we have the y by dx is the reciprocal of dx by dy, up here I've got dx by dy, therefore the y by dx is the reciprocal of this term here, so 1 on the square root of 1 take x squared. And once again, while that is not a fraction, it does function as a fraction. If you were to invert that function, you invert that expression there to get this term here. Once again, we have our domain is between -1 and +1. Now, if that's what dy by dx equals, if you were to integrate that expression, then you get the original y expression, which is arc sine of x. So that leads us to the integral of 1 on root 1 take x squared is the arc sine of x plus c. Now the same can be done for the arc cos function. So once again, you can express x as the cos of y. Then what we can do is differentiate with respect to y. We get dx on dy, the cos becomes minus sine. Now replace sine y by the square root of 1 take cos squared of y. Cos y we know is equal to x. That becomes 1 take x squared. And then, using what we've seen previously, then we can work out dy by dx is the reciprocal of that expression there. And once again, our domain for that function is the range of the original cos curve. Alright, and the same for arctan. So we can rearrange to get x equals tan of y. Now, we know that if we differentiate tan, we get sec squared. And we've seen from the previous exercise that sec squared equals 1 plus tan squared. That was question 12 in the previous exercise. So, I know that tan y is equal to x. That becomes 1 plus x squared. And once again, the reciprocal of this gives us dy by dx. So we have 1 on 1 plus x squared. So, these three here, you will not remember those. You will have them on your help notes. So you have this expression. If we integrate it, we get arc sine, etc. So, what about something more complex where we have not just an angle of x as we do in these three cases? What about x divided by a? Well, from our book we end up with this expression here. So we know that the integral of 1 on root a squared take x squared gives us arc sine x on a, but I'll show that on the next page. So if we begin with that there, then we know that x divided by a is going to equal the sine of y, same as previous problems we've done. So if I make x the subject, x equals a times by the sine of y. Alright, so if I were to differentiate with respect to y, I get dx on dy, and that will equal, now if I differentiate sine, get cos, so it's going to be a cos of y. And as before, we'll replace cos y by the square root of 1 take sine squared of y, and then we can use the fact that that rearranged would give me sine y is equal to x divided by a. So down here I've got a times by the square root of 1 take x squared on a squared. Now I'm going to bring that a into my square root term. So a becomes a squared when we put it underneath the square root. So let's write all this down here. So that's under the 1 square root. So therefore we end up with dx by dy is going to equal, if I expand my brackets down here, I'll get a squared take x squared, because the a squared here and the a squared there will cancel out, under the square root. Which therefore means dy by dx is the reciprocal, which is 1 on the square root of a squared take x squared, which is what we have up here. Okay, so that gives us another formula. So that one there, we can do the same sort of process, and we can end up showing that these become these terms here. So once again, you won't remember these. You'll need to access them. You'll need to recognize them potentially when you do problems. Okay, so looking at these problems here. For part A, then I can see that is in fact this formula here. So that value of 3, we could take that out the front and have a multiple, and therefore we just still got the 1 on root 1 take x squared. So we end up with 3 timesing the arc sine of x plus c. Alright, the next one, part B. Just notice all these ones here have a 1 as the first term, whereas these ones on this side here have a squared involved. So in this case here, a is going to equal in fact 4. So for part B, we would have the pattern is this pattern here. So we're going to end up with a value of the arc cos of x divided by a, which is now x divided by 4. Wouldn't hurt to put it in brackets, plus the constant of c. Now for part C, this looks like that one there. Notice you've got the 9 plus x squared, so a must equal 3, but on top I don't have 3, but I do have 3 times by 4. So what I can do is I can rewrite that as 4 by 3 on, and I've got 3 squared plus x squared. As for the first question, that's a multiple of 4. I can bring out the front, and I've just got my 3 on 3 squared plus x squared. Integrate with respect to x. So now using this pattern here, I'll have an answer of 4, and then the arc tan of x divided by a, which is x divided by 3, plus our constant of c. Alright, working out the definite integral. So once again, it's a matter of recognizing that pattern there. So we've got a is equal to 2 in this case. And if we go back, it is in fact that pattern there, which gives us the arc sine of x on a. So we end up with this becoming the arc sine of x divided by a, where a was equal to 2. We don't need the plus c here because we'll have a plus c and a take c cancelling out with each other. So we have between root 3 and 1. So substitute the root 3 first in place of x. We get the arc sine of root 3 on 2. Take away the arc sine of 1 on 2. So, working out this, arc sine of root 3 on 2 means work out the angle if the ratio is root 3 on 2. So, if we look at our table of values for the first quadrant, the sine of pi on 3 gives us root 3 on 2. Likewise here, what trig ratio results in a half? So the angle would have to be pi on 6. And that's all in your table of values for the first quadrant. So that's 60 degrees, take away 30, which is 30, or pi on 6 is my solution. Alright, that is exercise 7b. Have a go.